So my name is Ala Shiban, and I'm going to be talking about adaptive architectures and the end of microservices. And hopefully by the end of the talk, I will convince you that at least we should consider a different architecture. I grew up on Commodore 64s with cassette tapes. I used to work for Microsoft as one of the product managers on Visual Studio, and then led the cloud services org at Riot Games. And now the startup founder for Klotho. You can visit at klo.dev, which I know in German sounds interesting. And if you haven't heard of Riot Games, it is a game company that used to have just one game. Now it has a few other big ones. There's more than 200 million players worldwide. It invented esports, so it fills out stadiums with 40,000 people to watch other players playing games. $1.7 billion a year revenue. Two of the most watched games in the world. Over 1,000 engineers and an infrastructure org of over 120 people, out of which about 50 people in the platform engineering or the cloud services org. So that's kind of for context on Riot. So we're going to talk about why the end of microservices and adaptive architectures, infrastructure from code, or universal backends, depending on who you ask. And then I'll show you a live demo of something, how that kind of works in practice. Philip did a fantastic job for talking about microservices and monoliths, what works well, what doesn't work well, kind of the trade-offs. And how many of you have read an article sometime in the last year about why monoliths are better than microservices? How many of you have read at some point an article that says microservices are better than monoliths? And this conversation kind of keeps coming back up and up and up. And the truth is, it depends, it's a trade-off, and there's reasons why both existed and still exist. But each has positives and negatives. Microservices looks nice, and kind of every little box can do different things. What's easier? Separating responsibilities across teams. Scaling smaller units is easier. And then, limiting, because it's all related to size, limiting the blast radius of something is easier. What's harder? A lot of things are harder. In reality, it looks more like this. We have managing deployments, lifecycle is harder, shipping full versions. Again, Philip did a fantastic job kind of introing this talk. And there's service discovery and communication, distributed configuration, and all these extra things that come with microservices. And it looks more like this in reality, where it sounds easy, but it takes more effort. What's good about monoliths? So before we do that, think of microservices as the assembly code of the cloud. It's building blocks. And so far, we've been writing assembly. Monoliths have fantastic tooling. You F5, you git clone, you F5, it runs. You don't need to set up extra things or have simulators or cloud environments. It just works. So productivity is really high. You can hire somebody and have them start working on the code base that everybody works on within a day or two, rather than microservices where I've seen ramp-ups take at least a month to 4 months for developers. It's much more feature dev focused because of that. There's no service discovery. There's no needing to figure out distributed systems. It just works. Scaling is easier when it comes to taking the actual thing and scaling all of it up or to the sides. Once you start needing to scale smaller pieces, it gets harder. What's also harder is having faster deployments. Because of the nature of monoliths, you're shipping the entire thing everywhere. So as the code base grows, as you add more things, as you have a machine learning model in the thing, now you have a larger package which goes everywhere. We don't like that. Blast radius, we talked about it. Basically, one of the things that happened often is you change code, it breaks somebody else's build because it's harder to have isolation within a monolith. And organizational boundaries. One of the things that we don't talk about a lot is the cultural aspect of microservices versus monoliths, it's easier to just split repos and say, I own these things, you own those things. In a monolith world, how do we define the boundaries across organizations? And how does the promise go? We've been promised this for a long, long time. Just focus on the application. Something, insert word here, will manage the infra or everything else for you. And it used to look something like this. Like we've had so many iterations of this over time, whether it's moving to the internet or VM, microservices, containers, Mesos, serverless, and now Kubernetes. It's a never-ending cycle. As much as we want to believe that this is just the last time, this is not the last time. And it takes so much effort to build things. This is a small list of running something in a cloud setting, just actually setting the applications to the point where I have this sentence there that just has nothing to do with this, and it's hard to notice it because we expect this complexity. What is the impact of this? The impact of this is that, on average, based on the research we've done with mid-sized companies and fast-growing startups, around 63% only is left for feature development in organizations that move into a more distributed system. So almost 4 out of 10 engineers are not building for end users. They're enabling the rest. And it's not getting easier. Can we get the benefit of both microservices and monoliths, and some will say serverless, without paying the cost of each? Can we get the best of both worlds? We call that adaptive architectures. We've been working on this for about 2 years. Fundamentally, conceptually, we're saying that you get both benefits. So what that means is, what is adaptive in it? There's the topological aspect of the adaptivity, meaning you can have different shapes of architectures. It's not just one service or multiple services. It can change. And there is also adaptivity around technologies. It doesn't have to be Lambdas or Kubernetes or all the way from high-level compute units to all the way down to the network or communication stack, Linkerd, gRPC. It shouldn't and can't matter. It has to be a superset. Therefore, it has to be able to simulate or be the same as everything else that exists within the microservice and monolith world. The topological aspect of it isn't just about the shape, but also the ability or the technologies powering the different systems, but the ability to reshape your architecture. So you can start from one service and without changing code, be able to reshape how the application runs in a cloud setting. In practice, what this means is a developer writes plain code, adds something small to the code base in one shape or the other, or not necessarily the code base, but adds something extra. And then a tool, we'll call it a compiler or compiler optimizer, takes that code, understands it, and then produces an architecture. So it produces a monolithic application or produces a microservice-based application or whatever other architecture that the compiler deems appropriate for the setting or with your guidance. To make it a little bit more academic, I'll show this. I won't talk about this. This is kind of roughly how things look like in a more compiler optimizer-based world where you write plain code. You have parsers, you have language-agnostic transformers, different architectures. It's in the appendix. I'm happy to talk about it in the end. And I'll talk about naming. So we talk about adaptive architectures, and that's the aspect of the architecture itself. But the tooling for what actually happens has gotten a name in the community that I'll talk about in a second. But you know what infrastructure as code is. So if I expand this, it's infrastructure representation as code, or YAML. That's what IAC stands for, which its purpose is to take this kind of representation and produce this. This is a real example of this equals this. What's the alternative? What would an alternative look like? The name that this got is infrastructure from code. We don't like that name. You'll see why. But what this means is infrastructure inferred from application code. That's what it stands for. And the reason we don't like it is that it doesn't focus on the value prop, which is being able to write application code that doesn't have infrastructure tie-ins. So here's an example, very simple example of a specific tool. It happens to be ours, but there's many variations of this based on the infra from code type of tool. What this does is it has just a Python application. This is a plain application, no extra SDKs, no magic, no servers. Fast API-based, Redis, you can see its usage, plain. The tool that I'm describing here is called Klotho. And what we do with Redis is we add an annotation that says persist. Persist that Redis client in a cloud setting. That's all. For the API, we say expose this API to somewhere, in this case, publicly to the internet. And that's it. No extra files, no SDKs, no spec files. Your code is the spec. What this enables, the value prop behind this, is being able to write universal backend code that developers write using a simpler annotation, or whether it's in code or out of code or some hybrid, doesn't really matter much. And then the operations or the infrastructure group has the ability to set guardrails, has the ability to configure the compiler, has the ability to decide which knobs and movements to have, but they don't have to manage and write the specific how it gets implemented. That's the compiler. Okay, let me show you something in practice. I'll keep this here. Let's do it live. Okay, so this is a plain, let me zoom in a little, might be easier. This is a plain Node.js application or TypeScript application. We support Python, GoLang, C#, Java, not yet. And let me run it locally. Again, this is an adaptive architecture-based infrastructure as from code-based application, which means in our case, it's a plain application. So I'm going to run it locally. And I'm just going to curl localhost. And you'll see me sending in this image, which I will show you. Oh, I think I have like slides for every demo slide to give you context on what we're doing. Okay, we're building this simple, or we have this simple application that runs locally, which takes images and OCRs them and gives you back the text in it. Straightforward, simulates everything running in process for a real application. So, and what we want to do is eventually have this architecture built. And we'll do it in 5 minutes. And in the end, I'll show you the adaptivity part of it, which is taking those 2 lambdas and running them on Kubernetes. Let's do the basics. So like I mentioned, this is a plain Node application, so we're running it locally. That's the URL of the image. I will open it. Here we go. I think it didn't copy the URL correctly. That's the image. So we will send it to the recognize endpoint, running locally. It'll do some things. It's downloading a machine learning model, which I didn't consider. That could be a problem. It isn't. Great. So it OCR'd the image text. Let's make this a cloud application. Remember, no SDKs, no binaries, no magic runtimes, just plain code. Plus that little extra something, which in our case is those annotations. So let's go to the main index.js, where we have our fast API or our Express server. And on the listen command, I'm going to add the expose capability, which looks like this. We want it to be public, and we'll call this my API. And now that's it. We're done. What does that mean? Let me run the compiler. So now we run Klotho. If I remember the command, npx. So first, we compile the TypeScript code into JavaScript, and then we tell Klotho to compile this application, give it a name, which is the unit that binds everything together, and target AWS. Let's give it a new name so we are not cheating. Klotho runs, analyzes the code. It's a static analysis compiler. And then we can look into this compiled folder, which has everything you need to run, deploy, and operate your application without Klotho. What this means is that there's the infrastructure as code. In this case, it's Pulumi. It can be Terraform. It can be cross-plane. It doesn't really matter. It's just a translation language for us. It's the assembly code. And it has everything you need here. And it has a slightly modified version of the application, which I think because I didn't clean my folder before, it has some extra things. But for now, we take the application code and we inject or surgically change the points where we need to shim out what used to be local calls or local operations into cloud operations. There's no magic. It's just engineering, right? OK, so now, and there's a nice little image in that compiled folder called, well, this is kind of weird. This is the end state. So let's delete everything. OK, and then let me make sure that the code is, yep, this is not the end state. So we will rerun the compiler. And we'll get the compiled folder. And look at the image, which, again, is wrong. Do it live. Let's see. Oh, I know why. The TypeScript isn't probably compiling. So let me delete the dist folder and the compiled folder. And now I'll double check that we don't have any extra annotations. Yep. And this is part of the beauty of it. You find these out in build time, not after you build or after you deploy. That's the power of compilers. They give you certain guarantees that you couldn't have beforehand. Interesting. Let's try one more thing, TSC. Let's debug. We'll look at the compiled, the dist folder. I see why. I have this extra folder here that shouldn't be here, which I assumed won't affect things. But I think it did. So now, let's do this again. OK, and now let's look into the compiled folder and look at the image. And we got what we wanted. OK? This is ready for deployment right now. We go into the compiled folder, and we do Pulumi up, and this deploys. Pulumi, if you haven't used it, basically Terraform as code, or a variation of that, or like CDK, I guess. Cool. So we did the basics. Now, let's get serious, because this is nice, but this is a toy. Let's add some persistence. We'll go to our application, and I'll show you where we're saving data. So we have the OCR router. We'll go here. This is the kind of the monolithic benefit. Your editor, just the tooling works. You can go to right-click, go to definition. You can scan it. You can find all the things that you're building your application locally. And in here, we see that we are recognizing text. Let's go in here. And here we have the status map, which we are saving and reading data from. Let's find what that is. It comes from here. And in this case, it's just an ES6 map, a normal map. Let's give it the persist capability. And what this means is, the intent behind it is, I want this in a cloud setting to be persisted. Let's call this my results repo. And then rerun Klotho. And if I quickly open that image, which I won't, okay. Let's put this to the side. We just built a fully persisted, or an application that runs in the cloud setting with data, persisted, and a runtime, and an API gateway. So this is basically a serverless application that we built in minutes, without learning much. Okay, let's get more serious. Now we want to separate services, right? At some point, the application grows larger. This is the microservices story, right? We want to have smaller boundaries. We want to deploy different units separately. We want to have limited, more isolated units which can blow up separately. So let's do it. How do we do it in this world? In the index.ts file, kind of the main router, you see these modules being imported. One of them is the API router, so let's go in here. You see the basic kind of API, which has the results endpoint. And what we're going to do is we're going to add the execution unit capability. The execution unit capability is one of the more interesting ones, where it says this code runs in a separate execution unit, a Lambda, a container, a VM. It doesn't really matter, but they're together. And we'll call this my main router. Again, the names are arbitrary. There's no relationship between folder structures and magic things. They are logical. Now let's go to the other router. So we'll go to the OCR router. And there's two things here. There's the actual recognition, which is in a different file, and the API router. So I'm going to add the execution unit and call this my OCR router. And then I'm going to go to the text handler, to the recognize text function. And in here, this is where the actual machine learning model runs and the recognition happens. I'm going to add another execution unit and call this my compute ML. Okay. Now that we're done, let's rerun compiler. And we built a multi-service application that just runs. Okay, this is nice, but this is not a popular pattern for at least serverless things, or in general, because it has to wait for the machine learning model to finish. So let's add some asynchronicity to it. We want to have a event-driven architecture. So let's do that. So we go back in here, and then instead of recognizing the text in here, instead of asking recognize text, we're going to comment this out and use a version that is based on an emitter. So this is standard, in this case, Node.js, events, handlers, sending message passing. What is this object? I can use my fantastic, I need to define it first. So let's go to the emitter file. Oh, it's already there. So maybe VS Code just needs another run. Because it's just a monolithic application, which, oh, we can't see the hover over. Oh, no, we can. I can just import it, right? This is standard programming. There's nothing special here. That's the beauty of being able to do this. OK, so we imported the emitter. And we're sending an event that says, recognize with this URL. Cool, we're done. The API goes back and says, I'm recognizing. Fantastic. Let's now go to the results one, where we read the results. I think actually we don't need that part. We need the handler, which is in here. And I'm going to uncomment this, which is just an event handler. It says, whenever somebody sends me a recognize event, grab the URL, and then recognize the text. And recognize text will save it in that status map. It doesn't know what this file is or module is. We'll import it into this file too. Done. Now, how do we tell the compiler that this mechanism, this event handler, is actually a cloud event handler? Let's give it the persist or the pub/sub capability. And we'll call it my stuff. Yeah. We'll recompile the application. And we just built a cloud-native, multi-service, async application. How much time would this have taken to build in any of the tooling that exists today? Can anybody build this in a day? I would argue that this takes quite a while. OK, so we talked about this, but we haven't really talked about adaptivity. So let's see adaptivity. With every compilation, we produce that Klotho.yaml. This is a configuration file. This is not a spec. So this is auto-generated. And it has all the different settings that we, as a compiler, have used as defaults. Now, you can also pass, depending on the target infrastructure as code framework, configurations straight from those frameworks. So you're not dependent on a spec that we create. You might break us because you're using a feature in Terraform or Pulumi or others that we don't account for, but that's OK. That's the trade-off. And it's additive, which means that I can delete everything I don't care about. So I'm going to delete everything in here. And delete everything in here. I'm also going to delete all the configurations because they're additive, and these are the defaults. And you'll see that every execution unit that we defined has an entry. So let's change this. OCR router, we want it to be which is in here. Let's make this EKS-based. And my main router, let's make this EKS2. I don't know, is this how we? Yeah. Perfect. Now we rerun the compiler, and we just say, use this config file. Now, because the compiled folder is ephemeral, it is designed to be. You can check it in if you want, and you get a snapshot of the entire application, all the services, all the different pieces. Or you can just rerun the compiler. So to keep that, we just copy this file out. And now we'll say, use that as configuration. And we're done. It'll set up Kubernetes clusters or import them if you want. You can configure that in. You already have a cluster. It'll set up all the different tooling. It'll use the Kubernetes APIs to call the different services. It'll have service discovery. It's all built in. We shim out function calls, event handlers, all the different programming language constructs. We already have service discovery in programming languages. They're called functions. We already have message passing. They're called events or different libraries or existing open source software like Redis or others. They already exist. We don't have to have the same semantics, but in some cases, there are different runtime characteristics, like first in, first out, or what kind of retries. Those are the things that if they don't exist on the programming language natively level, then we have to add that metadata, whether it's through some OSS library that we can parse, or through either an annotation or a configuration that comes from somewhere else. That's the extra something that I talked about. That's it. If I go back to the Lambda version, because this would take time to deploy, because we would be deploying a full cluster. Can probably just delete this file. And I will rerun the compiler. I'm going to be cautious and just delete the entire compiled folder and rerun the compiler. And then go into the compiled folder. And I'm going to do npm install for the Pulumi dependencies, because we're going to try and deploy this. Which is, I would say, the more riskier part, especially with the internet speed. So we'll try the alternatives too. And that's kind of the power of infrastructure from code. Your code is the spec. You don't have to add the same metadata about routes, about if you're using Redis, it should understand that there has to be a Redis backing it. Defining it outside of it is just adding more context or repeating the same context. Now, in the code, you're not defining the infrastructure. It's already there in the sense that the usage of the tool dictates that it has to have a backing store for it. So I'm going to do Pulumi config US East 1, and we're going to call this stackconf 3. I'm going to do Pulumi up. And you'll see the plan that Klotho generated for this code, or the cloud version of your application, or our application. You'll see the Lambda definitions. You'll see the different methods. You'll see the different computes, roles, permissions. It is least permissions by default, because only the things that have arrows between them can access one another, so you get extra security as part of the analysis of the code. And we'll say yes. Now, this will take 4 minutes. I will run a version that we've deployed before. I think it's here. So I will show you the, oh, no, this is a different application. Let's try it here. Another different application, so let's just open a window. Local versions, and you see that it's the same calls. The only thing that I changed is, I actually can just show the output of the last run to show you kind of what comes out the other end, which I can't, I guess. Let's see, because I cleared it. Okay, hopefully it'll finish deploying, but I will send the request. It will tell us that it's recognizing the text, just like it did locally. And then we'll do another curl to hit the recognize endpoint. And I will just copy. You see that the commands are the same as the local version. So I'm just replacing the local URLs with the online URLs. I think this is the result one. It already has it in it. And it's still processing or waking up the Lambda. Same application, same behavior, runs in a cloud setting, event-driven, async, took us less than 15 minutes to build, and maybe deploy if it's finished on time. So that's kind of roughly what a solution that is from the family of infrastructure from code would look like. There's others. Ours is not the only tool. So how do different infrastructure from code solutions differ? Languages, not everybody supports all languages or most of the languages. Because it's a compiler-based approach, writing parsers is actually a harder job. And especially once you start talking about multiple services, the execution unit, the annotations in general, or any kind of system that tries to understand and decipher what the application looks like, has to work together. So all the, in our case, annotations, they interact with one another, and that's where the complexity comes from. And that's per language. The names are, so ours is Klotho, there's Nitric, Modal, Shuttle, WingLang, Encore, and Service Weaver that came from a small team at Google. There's more and more of these solutions which are compiler-based. I talked about annotations, but different startups are doing different solutions or different approaches. We use annotations. Some use SDKs, so the usage of the SDK is what drives their compiler or their tooling, either at build time or at deployment time. Some are building entire languages. So WingLang, if you've heard of them, are building what they call infrastructure in code. And so that explicitly combines the infrastructure definition with the code. So it's a lower level abstraction. You actually write buckets and the different queues, et cetera, or specific queues. And there's hybrids that combine SDKs with kind of annotations, and that's Shuttle and Encore. One of the most powerful aspects of this is because it's analyzed at compile time, we are able to infer what permissions are necessary or which parts of the application is allowed to access other parts of the application. And that avoids either the ops folks or the infrastructure team or the developers to actually define manually what is the permissioning model that you need to define, because you already have that information in the usage. Configuration is an interesting one. If you want to be able to use Terraform configurations or Pulumi or Crossplane, one of the things that a lot of tools wind up doing is creating their own interface or their own spec. So you don't have to fill out the Terraform spec, but you have to fill out their spec, which is basically mirroring the Terraform spec, because that's what they do. And so what we try and do is pass things through from the infrastructure or from the configuration, same standard, reusing effectively the same underlying infra as code framework at the cost of potentially getting broken. Others have some form of a wrapper around that configuration, which effectively allows the infra team or the developers to describe what that relationship, the mapping between top level and low level is. And then others, we don't know. So tech interchangeability, and that's a big one. That's what we believe in, the adaptivity of it. We built a system that is fully adaptive, all the way up from compute, all the way down to the communication layer. It's designed that way. Some are saying they will get there, but in most cases, the other solutions, what they will do is they will say on Google Cloud, we use for relational database, we use Google SQL or whatever the version there is. On AWS's thing, we support RDS with Postgres. And for compute, we support Lambdas. And Encore supports Kubernetes. So it's a pre-selected set of technologies rather than being able to interchange the different elements. What I want you to take away from this is the conversation around microservices versus monoliths. We have to get past that. It's about creating a new architecture that has the benefits of both without the cost. Now, there's trade-offs. Of course, there's trade-offs, especially with compilers. For years, we've heard things like Java is not going to be fast enough. It's not going to be expressive enough. It doesn't even have pointer arithmetics. C++ will stay with us forever. And then X years later, who's writing C++ unless you have to? Right? There's always going to be people that will write assembly code because you have to optimize and you have to understand the underlying layers. But compilers will keep improving to the point where you don't need to, or at least a big chunk of people won't need to. That is that is the direction we think things will go with or go towards. The adaptivity comes at the cost of being, or adaptivity is about being a superset. The worst case scenario in an adaptive architecture has to be how you do it today in either microservice land or monolith land. That's the worst case. You do the exact same thing. That's what makes it a superset. The best case scenario is you don't have to do it at all, or you do it really simply. And infra from code solutions, they're there now. So in our case, we've been in production for about 1.5 years. It runs real large-scale workloads. It's really interesting to see how you patch the infrastructure as code, how you patch the runtime components, how you patch the application. Because it's just source-based, there's no hidden components, there's no server, there's no magic black box. It's all just source. And so there's different solutions for, and different questions for observability, for how do you rev things, how do you version things. In many cases, they're the same as how we do it today. When you have something like this, you check in the code, and that's a version because it's the entire application. We've solved versioning. If you want multiple or different groups owning different components, it's called modules, which can be versioned. We've solved that problem. So there's interesting things that happen when you start talking about how to take a programming language and making it cloud native. That's it. Questions? Please ask questions.
Are there any questions in the moment?
What do you think the problems with this or with this approach are?
Yes, when you have to speak into the microphone. So when we see the video later, we can hear you.
So the way I understand it, the main change with the complexity is that you're shifting it away from runtime to a build time. Because in this case, like in the problems that you ran into, you had to sort of delete folders that had old stale files that then would interfere with the new ones. So that's the main trade-off by using something like this over the existing, is that you're moving the complexity away from the cloud, essentially, to your build step.
The powerful thing about compilers is that it gives you guarantees at build time. We try to, so yes, it introduces other types of complexities in runtime. The key aspect to that also is today, a lot of the solutions that you get move complexity from one place to the other. Look how easy this Kubernetes abstraction is. Just fill out our spec. Don't fill out this other spec. But the minute you break out of the abstraction that this simplified version has done, then you're now back into microservice hell. And so what we try and do with the compiler approach is absorbing the complexity, not streamlining it. That's kind of conceptually how we try and define it. But yes, do as much as possible, guaranteed in the compiler step. I didn't talk about optimization, which is an interesting continuation of this story. Being able to get data back from the runtime post-deployment aspect and feeding it back into the compiler to optimize, but obviously that's where the next step would be.
Anything else?
And what is the debugging story with this? So I'm going to draw an example because this I originally come from JavaScript world, so this reminds me very much on like Webpack, and you sort of minify your source, and the code that you run is different than the code that you write. And the main challenge that you run into these is then the code that you debug is the code that you actually run, not the code that you originally wrote. So yeah, basically, I imagine similar cases could be here as well.
Perfect. By the way, this is the deployed version that we built. It finished, gave us a URL back. But to answer your question, let me show you the before and after compilation. So the source, the JavaScript version of the code, and the compiled version of the code. So I'm going to go in here, and let's take status is too simple. This is too simple. Maybe not too simple. OK, let's do this one. I'm going to put this in here. And then I'm going to go to the compiled folder. And then I'm going to open the same file. So this lives in the main, I'm assuming, main router. It actually exists in all of them because it's a shared module. I'm going to put this in here. So now I want you to tell me what's different. On the left is the plain JavaScript locally running application. On the right is the compiled, cloud-compiled Klotho version. What's different? I will tell you a secret. Nothing. They're nearly identical. How does that work? We try and separate as much as possible the implementation or what you've written versus what we've changed to have maximal recognizability in production. Because nobody wants to be able to go and run or load source maps or all of those things. So we try and maximize that. If you look on the right side, what this actually is, you'll see that in this case, the Dynamo call, so let's go in here so we can show these two files too. So those are identical to, am I looking at the right file? Yeah. OK, oh, the annotation. So if you look at this here, you'll see the writing and reading from the data set. Again, on the left, this is a local memory call. On the right, this should be Dynamo. And so if you go in here, you'll see that the main difference is the status object. And instead of the default ES6 map, we just change it into a Klotho runtime file. Same interfaces, minimal change, fully source-based, so you can right-click, see the source, patch it, change it, fix it, keep your version of it. That's how you inspect the code. Debugging, because this is a compiler-based approach, you can have a plugin for Datadog or OpenTelemetry and effectively say, I want this application to be instrumented with Datadog. And we will go, that plugin will look at the entirety of the application and instrument automatically for distributed tracing. Fundamentally, we want you to be able to continue using the same tools the same way you use them today. It's a superset. It has to be that way. But the benefit is that you don't have to go and retrofit every service to get that value. You just get something that understands the semantic tree, which we expose to the plugins, and then they go and they instrument every piece. Same thing with being able to simulate this locally. Same thing with fault injection testing. Because now it's super easy to do these things once you have plugins that support them. So the barrier to entry to use those services gets much lower. Portability gives you negotiation power as an organization, because now just having a plugin-based system allows you to switch out New Relic to Datadog to OpenTelemetry with nearly zero effort. You just change the plugin, recompile, all the instrumentation across the application changes. And now you can renegotiate.
All right, let's wrap it up here. I'm sure you will be available for more questions.
Yes, so I'll be outside or
yes. So let's make some noise. Thank you very much for your very interesting talk, Ala.